There we go.
Well, I'm going to start with actual Gödel's argument. Before we start with his actual argument, we have to go through a set of tools that he uses to even start to talk about what the argument is about. So, first of all, we will talk about Gödel's numbering. Very, very generally, what Godel does is take every single statement in Principia Mathematica and it maps it into a number and then uses the properties of those numbers to talk about the statements themselves. So we were going to start with, first of all, you can see here I already pre-wrote the actual pairing that it does. So I'll give you an example just to give you an idea of exactly how this process is made. So imagine we have this statement. Again, this is absolutely meaningless. But for our mathematical understanding of this, this means, well, not 0 is equal to 1, right? Some true, this should be deducible by PM, right? What number would be assigned to this? So the first thing we do is we assign every single symbol to a number, There we have it. And so we can assign, well, this one is 1, 7, it's not 7, 8, 6, 5, 7, 6, 9, right? Every single symbol is paired to a number. And then what we do with that is now we're going to take every single prime, we're going to put it in order, and we're going to raise that prime to the power of the symbol that we assigned. So 5, 7, right? And then we just literally multiply all of them, right? And this number, I'm just going to call it x, this very big number, is going to be the one assigned to this one. And so, why is this even useful? Well, we want, the reason for the map, we'll see it later, but we want a single number to represent all the information that we have about this statement, right? And the only two pieces of information that we actually have, that we need, is we need the symbol, right? We need to know exactly what symbols we're using, and that is encoded in the exponents. And the other piece of information is the order of the symbols. And that is encoded in the primes. Specifically because the primes are put in order, right? This mapping, we're just going to call it some function G, okay, that maps statements in PM to numbers in, like, literal numbers. And what we know about this pairing, first of all, that is very important, is that it is injective. And the reason G is injective is because every single statement will have a specific numbering. Like, basically comes from the properties of natural numbers. That is, every single natural number, no matter how big, will have a unique factorization. And that unique factorization will have, if put in order, a unique set of exponents. And that set of exponents will lead you directly to the statement itself. So in that sense, we're not losing any piece of information, and we know that it's injective. So we make sure that every single statement in PM will have a unique representation as a Godel number. And also mentioning the things of statements that don't make sense, because of that, DSG is not surjective. Because, for instance, if we have number 18 and n, we know that's just 2 times 3 to a 2. And if we were to understand that, like, translate it back into Godel's number, that would just be like not 4. And that makes no sense. So not every single natural number is a Godel number, basically. So once we understand this, not only very small note, also not only can we map single statements, we can also map series of statements. The way we do that is basically, imagine we have some statement, not statement, a number. This is a number that represents a statement, right? Imagine we have A1, A2, some n statements, okay, where L of AI is an n. Specifically, Godel number n, okay? And all of these are numbers that for us represent statements, right? We can still encode series of them by simply taking that very number and doing again the thing with the primes, just taking every single prime and putting it to the power of that very big number. This is a even bigger number, okay? This is the nth prime to the power of that one. And then we'll give you one even bigger number, but that still doesn't actually interfere with the ones we have before, because every single a is going to be bigger than 12, so it's not going to interfere with them. And every single a is composite, so it's not going to be a set of primes that we have here. That, by the way, we can also use variables. We can actually have an infinite amount of sets of variables by simply giving every single variable a prime number, so it will interfere with each other, and then primes to powers, so that we have a unique map from symbols to natural numbers, and then using those symbols to create other natural numbers so that we can have the G function. Right? Any questions? No?
What was the reasoning for there being no interference again between first and second?
The reason this set of numbers doesn't really interfere with this one's is because every single exponent here will be bigger than 12. Okay, so we will not be able to confuse. If we have a 12 in the exponent, we know it's not going to be a statement, because we don't know it's not going to be a statement because there is no statement that is smaller than 12, because a single one of these by its own doesn't make sense in PM. So you're not going to encounter one of these by its own, and all of them are composite, because there doesn't exist a statement in PM that is a pure prime number. No, sorry, because every single symbol is in itself either from 1 to 12 or a prime or a power of prime. And since it's composite of various, more than one prime, that's kind of what I'm trying to say, it wouldn't really interfere. Do you get it now?
Yeah.
Okay. It's not that important. Just it actually doesn't interfere with each other. Okay. So you may be wondering, okay, why is this map even useful?
So Claudia, can I ask a question? So why do you differentiate between lowercase alphabet letters and these uppercase?
Oh, well, sorry, I didn't explain that. Basically, we can have, in logic, it's very common to have different levels of types of variables. So for example, in this one, these variables specifically, I will be using only to represent numbers. These are all numerical variables, and they are assigned to the primes to the power of 1. P, Q, and R represent statements, meaning they can be, a whole statement in PM can be understood through only P. You know, stuff like P or P implies P, right? I could put any statement in there and that will still be true, right? This is a propositional statement of logic. And this one, I forgot exactly what this one maps to. I think it's, what was it? Maybe groups of statements? I'm not sure, but this is a higher order of reference. The whole point is that we can continue doing this for any series of notation that we actually want to make. So we're not restricted. Is that?
Sure,
okay.
Sure.
So now we're going to see exactly why this is so useful. And the thing is, this map actually allows us to take a very big step. That is, not only this map, PM formalizes mathematics or number theory, but the Godel numbering allows us to formalize metamathematical notions, right? So this is the formalization of mathematics. Right, so what does that mean? Metamathematics is talking about the statements of PM, talking about the statements itself. How do we even formalize stuff like the structure of the symbols, what it means, all of these notions? We want a way of also formalizing them inside of PM. And in that sense, I'm only going to give you a glimpse of an example of how this can be done. Godel will use very much more complicated examples that I will not be able to necessarily prove, but this is just an example to give you an instance of how could this even be possible, right?
What was the highest level of statements that Gödel was working with?
Honestly, for this talk, I'm literally just going to use until here.
Oh, cool.
This was what was put in the book. I put it just for information purposes. Don't really care about them. Maybe these a little,
Yeah, propositional makes sense and numbers make sense. The other ones, I don't know how to
I
imagine.
completely forgot what these are for. I'm so sorry, but I'm gonna.
It's okay, it's okay.
It's fine. So let's consider the statement. This one is there exists a z such that. And can someone tell me what that means?
There exists a number.
Yeah.
Just read it.
In our mathematical understanding, this says, well, there exists a z such that 6 is equal to 2 times z, right? In other words, this literally just means 6 has a factor of 2. This is not mathematical. This is just a statement that we would like to be deducible in PM, right? Everyone understands how this is like a statement of PM. Okay. Now we're going to join it with this other statement that there doesn't exist a z such that 6 is equal to z times 4. Again, what we're saying here is 6 is a factor of 2 and not of 4. It doesn't have a factor of 4, right? Which is true. We would like this to be deducible in PM precisely because, well, 6 is, well, 2 times 3. So it is true. It has a factor of 2, not a factor of 4. Okay. But what happens if now I take, do you remember the one that I had, this statement? I forgot to actually put the number, but this, if you translate it to Godel numbering, this is, this has like, its Godel number, this is x is equal to some 3.84 blah, 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 times 10 to the 37. Very big number, okay? What happens if now, instead of just talking about this, we talk about that very number, which is again only it's just a number theoretical property, right? So instead of 6, we literally just put here that amount of s's before the 0, which no one is actually going to do it. This is just theoretically possible. We're just going to put here the actual, right? And we would also like this to be true because we know the factorization of that. We were the ones who created it, right? We know that this maps to 2 to the 1 times 3 to the whatever, times 5, 7, all the primes, and it's precisely we know that this big number has a factor of 2 and not of 4. But, however, in a mathematical understanding of this statement, not only is this statement saying something about this number, it is also saying something about this statement. Because knowing that this statement, that this number has a factor of 2 and not of 4 is exactly the same as saying that this symbol is the first symbol of, let's say this number, the of the statement with G number X. This is what we understand from this. So we gotta, this is actually, we're able to talk about the statements themselves only because of the number theoretical properties of their numbering. So saying that this is a factor of 2, not of 4, it is the same as saying the first symbol of the statement that it represents, its first symbol is in negative. Any questions? Yes? Okay. So this is just a glimpse of how one can even begin to talk about the statements themselves in PM. And the thing is, all of the properties of the statements are encoded in the numbers that we have given them. So stuff about them reduces to a number theoretical problem that we can then mirror in PM, right? And so now is where the more complex functions using these ideas begin, right? Gödel now uses and defines 2 functions. There are so much more unbelievably complex of what I have put right now. I'm not even sure if he even defines them, like gives an actual procedure of how to find them, but he does prove that they are possible to be constructed within PM, okay? The first one is the dem function. Dem function stands for demonstration, okay? The dem function basically has 2 inputs, It's not a function, by the way. It's a formula, but it has two inputs. That is here a sequence of statements, and here is a single statement. And when I say that, I don't actually mean that you put statements in here. It's just that they are numbers. The inputs are numbers, but those numbers represent, if we did if we decoded the numbers, X would be a sequence of statements and Z would be a single statement. And what is basically trying to say here is the sequence of formulas with Gödel number X is a proof of the formula with Gödel number Z. So what we're basically doing here is taking typographical relationships between the strings that they represent and mirroring them in number theory with purely numerical relations between the numbers X and Z. This is just a shortcut for a very long, very complicated statement in PM that talks about the relation between X and Z. There is a numerical relation between X and Z because think about how we have the axioms and we have ways of changing them. When we make those changes, and we pass them to like the Godel number, the relation between those exchanges is a number theoretical problem. The way they are manipulated has certain rules that we can map into PM and that become simple number theory problems. And so that connection is what Dem is actually trying to say. It's a long formula that talks about the properties of X and Z, and if that statement is deducible, if that long statement that this is a shortcut of is deducible, well, that means that in a metamathematical sense, the sequence of statements of X prove Z. Okay?
So just to understand, so this is analogous to So this is analogous to what you showed earlier with something having a factor of 2 but not a factor of 4.
It's analogous, but it's not really the same thing. But it's
right.
Like the example from above before is an example of how we can talk about these statements only from its Godel number. Right? And talking about them is only a number theoretical problem, so we can still map them in PM.
So this dem function or this dem formula, if I have dem of x comma z, and let's say that x does deduce z, then just the dem would be true. Is that?
Yeah, the long statement that this is a shortcut of, which is a number theoretical statement, would be deducible by PM.
Right, but I'm saying the output of this would be true.
It's not an output; it's a formula. This is not a function. Sorry. This is a formula of PM.
But what's the difference between having a formula and the function?
Well, this doesn't really output anything. This is just a shortcut for, like for example, for before, like this is a formula, right?
No, but the formula would be true if what's inside of it is deduced.
Well, yeah, well, precisely, it is true in our sense of like number theory, because Godel proved that a very specific types of function, which includes this one, are basically true and should be deducible by PM.
Nice. Okay.
But the one that I'm going to explain now, I think you're going to see the difference, is an actual function. It's not a formula, but it's also a little bit complicated to understand. So basically, if this is deducible, we know that X is the proof of Z, right? Now we take the other one, the subfunction. This one takes 3 inputs, which again are numbers. And basically what it's saying, which by the way, these are 3 like independent numbers. It says the Godel number of the statement with Godel number X, when all the symbols with Godel number Y are replaced with Godel number Z. I'm going to give you an example of this. This is a function that takes the properties of these and then outputs the Godel number of what would be the statement of taking the statement X, replacing every instance of the number Y with X. Let me give you an example. If you have this statement, right? This statement has some number X, and it's also a very big number. Is you can imagine a 7, 6, 5, 7, 17, and 9. If you follow the symbols from there, right? You raise all to the power of the different primes, okay? And that's going to be the value of X. So X is not the actual function. X is just the number that represents the function, right? And then we have some z, right? We're just gonna literally give it a number. All of them are numbers, right? This is just 2. And now we're gonna set, So we have this statement, and then what we're gonna do is basically take this statement and take every instance of y and substitute it by z, meaning this statement becomes this. Literally just taking z and putting it here, right? Its Gödel number, so we're gonna have it here, is gonna be equal to sub of x. This is what it's doing. It's talking about the properties that x, y, and z have in common as a way to output what would the Gödel number be if that were to happen, okay? This is our understanding of what is actually happening, but again, this is just a function, and these are only symbols, and they're just talking about numerical relations between x, y, and z, right? So, and just to give you a little glimpse of how something like that could even work, is basically just think that this first part, this whole part until here is going to be the same as this part here, right? The instance in which this prime has a 17 there. In this case, specifically, we're having a 17 here. We're setting y to be 17 specifically. When we find an instance of that, which we can do, we can just ask, oh, does this prime to 17 is a factor of this number? And is that to the power of 18 a factor of this number? Well, if it is, then we know that that specific prime represents the element of y that we want to substitute. And then here we substituted by z. So it's kind of like that. It's just to give you a glimpse of how one could even get the connection between all of these numbers to output that. But the whole point is, I cannot really prove why these actually work. There are very complicated proofs about it, but just to say, they are things that are legal to do. You can do this legally in PM, and it doesn't necessarily break. It's part of the set of theorems that should be reproducible, and Godel proved that in his correspondence lemma before, right? So now is when the actual argument starts. We've devised all the tools we need to now understand how Godel was even able to prove the things about the incompleteness and consistency of PM that now we're going to see the results of. So this is a 5-part proof. So we'll start with the first one. Wait. So we start with actual. Okay. So let's just consider this statement. That is, we will have the dem function of x and z. Okay, it just says x is a proof of z. If we say here, we put here there exists, it says, okay, there exists an x such that x proves z, meaning in our metamathematical understanding, there exists a proof of z, or z is deducible. Okay? If we put in negation, it's the opposite. Z is not deducible, or there doesn't exist a proof of z. This is a valid statement, and it should be either deducible or not in PM, given a specific variable for z. Right? Well, now we're going to take z. I'm going to give it a very specific string, a very specific number. That is going to be a subfunction of y, 17y. This is the statement that we're going to be working with. Okay? Y is a variable. We can put anything we want here. And the statement that represents, every instance of that statement that has a y will be replaced by the number itself. This is non-recursive. This is non-self-referential because, to some extent, because what we're putting again is an actual number. We're not putting the statement, we're putting a number. Where y is, we put a number. So it's kind of like a function in a way.
Sorry if I'm pressing you again. So dem of xz, the way I should understand that is a statement which says I can find a proof of z a proof X of Z.
Yes.
That's how I should think about it.
Yes.
Okay, cool.
This
cool.
this is a statement in PM.
Cool.
This should be deducible or not deducible because this here is a simple number.
Okay.
To be specific, there exists X, dem X stuff is
The-
there
You can
exists-
find an argument,
Yeah, just dem X that is X proves that.
Yeah, X is a
X
proof of Z.
demonstrates that. technically.
And what was
Problem.
sub again?
Sub is if you were this is a variable that's not been
Okay.
devised. Like you could have in another function sub this thing 17 2, and this statement would become precisely with a 2 instead of the y, right? Like this is basically a function. This is sorry, not a function, a formula in PM, and this is a number, specific number that then that number would represent a statement that we're saying does not have a proof. Yes? Okay. Bear with me. Bear with me. We don't really know exactly what Godel number this would have because of why, but we're just going to give it a number n. This is just n, okay? And now we're going to construct the other one, which is very interesting too. That is, we're going to get the same statement, but now, instead of putting y, we're going to put n. What is that saying exactly? Whatever this statement gets, whatever we give to this statement, n, we're going to put it here. We're going to put it here, and we're going to say, oh, there doesn't exist a proof of this number. So there doesn't exist a proof of this, right? And we don't really, we're going to name this statement G. And again, we don't really know what its Godel number is. We're just going to give it a small g, okay? And basically, what it's saying here is the formula with Godel number of this is not demonstrable. And in here, it's saying, well, the formula with Godel number of this is not demonstrable, okay? But now let's consider a different one, completely not unrelated, of course, but let's consider this one. Sub of n 17n. This, as you know, is a number, right? What number is it? Well, let's see what it says. It's saying, okay, let's take n. So let's just get n here, okay?
Hey, sorry.
Yes?
So is 17 supposed to be represented by, or y is supposed to be represented by 17, right?
Yes.
So you're taking all the y's and replacing it with y's?
No.
'Cause-
I'm taking every single instance of a y and I'm substituting it
No,
with
for
this one.
I meant just the sub
Yes.
y 17.
Not y. You're taking every instance of y and you're substituting by the number of y.
Which is 17.
No, exactly. When you would give, imagine you have another function that has sub n and has 2. Like instead of n, we just put here a 2.
Okay.
Right? Then the y's would get a 2 in here, and that's what basically it's saying is take the statement of 2, which actually doesn't have any meaning in PM because 2 is just
No.
negation.
Yeah.
Just take that, and for every instance of y, which has none, put y in it, which is 2, right? So if we were to have a y in that statement, we would just replace it by 2, which is not a y, so it would not be in any way recursive. This is just a number, you're just putting a number in it. You know what I mean?
Kind of. Sure.
Okay. Either way, let's just consider this statement for a sec, okay? Well, what is exactly saying to us? Was we want to figure out what its number, okay? Well, it's saying take n, so we take n here, and we take every single instance of the symbol of 17, that is y, and we replace it by n. We take this, and we replace it by n. This is what that is saying, which is precisely how we constructed this. This is exactly the same statement. So we know that that statement has to have Godel number of G. But wait a sec, if you see this now, that is G, and that is exactly the same as this. So this thing here also has a number Godel of G. So what is this exactly saying? This is saying, oh, there doesn't exist a proof of the statement with Godel number G, with this G. So basically this statement is saying is there doesn't exist a proof of G. And so we have constructed now a self-referential statement that talks about the lack of proving itself. And so now that's how basically everything breaks. Because now we have to question whether, well, is G demonstrable? Like, does there exist a proof of G? Because if we consider that, okay, G either has to be demonstrable or not, right? So if G is demonstrable, demonstrable, well then there exists a proof of G, which is precisely this part here, which is precisely the negation of G. So if G is demonstrable, then not G is demonstrable. Right? So, and we know that that can't be, because that is a contradiction that would lose our consistency. So it must be the opposite. That is, if not G is demonstrable. But if not G is demonstrable, then there doesn't exist a proof of G. Right? There doesn't exist a proof of G, which is precisely what G is saying. And so we conclude that G is demonstrable, because we've just demonstrated by the assumption. And so whatever value we give to G, it leads to a contradiction, right? Whatever, if we give a truth or a falsity value to G, that means that our system of PM is inconsistent, and we want to avoid that. So if PM is consistent, that implies that G is formally undecidable. If we want PM to be consistent, we cannot give a truth or false value to G. Simple as that. Okay. But now we wonder, from a mathematical perspective, what is G actually saying? G is saying that there doesn't exist a proof of G, and we know that that is true. We know that there doesn't exist a proof of G. We have found, therefore, a true statement that does not have a demonstration. And so if G, so we have found that if PM is consistent, then PM is incomplete. Because if, in a way, we have seen that the price of consistency is that we have to throw out completeness for the system of PM. And actually, I was saying how we can understand G to be true or not, but even if we were not gonna give it, if we didn't actually know what G is, we know that either G or not G has to be true. And we know that both of them don't have a demonstration, because if we assume they do, we lose consistency. So if we want consistency, regardless of the value of G, we will have incompleteness, right? And this is one of the biggest, like, this is the proof, one of the biggest results that Godel gives. Through the construction of G, he's able to prove the necessary incompleteness of PM, starting with its consistent, if we assume it is consistent, and we definitely want it to be consistent. And not only that, he also proved that PM is essentially incomplete. And by that, we mean that you're like, okay, if we cannot really prove G, but we want it to be true, then we could just put it as an axiom, because we don't have to prove those. The problem is that the subsequent subsequent augmented system that we create will have other arithmetic truths that are improvable, and he was able to prove that. So we know that we cannot really not do anything to prevent this self-referentiality from happening, only with the materials that we have, that is whole numbers, addition and multiplication. This is sufficient to disprove, to cause the incompleteness of the system, right? So this is one of the first main result, and now we're going to talk about the second main result. And that's, well, now we have this, right? We have this. We have, if PM is consistent, then PM is incomplete, right? The thing is, well, Godel also found that those statements themselves can be mirrored in PM itself, right? This part is a little more technical, and a lot of it I will not be able to prove, just to give you an idea of its last part of its two incompleteness theorems. So let's start with the consistent. How we can say that PM is consistent? Well, as I told you before, a if you look at the statement that P implies, not P, implies Q, that I told you before, this is provable in PM. This is a true statement. And it is the basis of, well, our reduction and sorting, basically. That is, if P is true and the negation of P is true, then Q. And Q can take anything. So what we only need to prove consistency is that there exists at least one statement that cannot be proven. Because if one statement cannot be proven, then there cannot exist any internal contradictions, because if not, that statement would be provable, right? So the equivalent to this is saying that there exists a Y such that there doesn't exist an X, such that demonstration of X. Okay, so there exists a statement that does not have a demonstration. Yes? This is equivalent to saying that PM is consistent. And that is a valid statement in PM. So that is how we can reference it. And then we're going to talk about PM being incomplete. Right? Well, the incompleteness of PM, it is the same as saying, well, there exists a number. Well, there exists a instance, a true statement that cannot be proven. And we know that there exists one. We know if there is an instance of it, we know that there must exist one. And we have one that is G precisely. This is a way that we can map like incompleteness in PM, right? Assuming all the time that it is consistent, right? So if it is consistent, we're saying, well, this thing that we're gonna name A, okay, we're saying, what Godel basically proved is that A implies G, right? Mathematically, he was able to prove that. However, since now we're able to talk about this statement in PM, not only was he able to talk about it mathematically, he was able to prove this in PM. In itself, within the system, it was able to prove that if PM is consistent, then it is incomplete, right? So that leads us directly to the main result. That is, well, this is deducible, right? And so if PM is consistent, so if PM is consistent, right? Well, then A being deducible in PM, then by the other statement that we've already proven that we know is also deducible, okay, that would imply G. And we know that G implies not G. And since we now have an internal contradiction, we know it's not consistent, so we know that A, that is the statement PM is consistent, is false. And so we have inconsistency, right? Basically, if we assume PM is consistent and we assume that we can prove A, then it breaks consistency again. What does this exactly mean? Well, what it's saying here is that if PM is consistent, then there doesn't exist a proof of consistency in PM. So basically, if we assume the consistency of PM, there exists no proof of its consistency within the bounds of PM, right? And so this completely breaks the project that these mathematicians had, because not only it is impossible to achieve incompleteness if we assume the consistency, which is something we want even before incompleteness, is that if we want the consistency, we know that we won't be able to find a consistent proof of it. Not a consistent proof, a proof of it, sorry. And just to give you, this is not a specific anomaly of PM. This is not because Russell and Whitehead were like, oh, they just constructed a bad formal system. These results speak to the very property of any formal system which has a sense of whole numbers, addition and multiplication. The way he constructed the proof, Godel, was so general that it would be able to be applied to any sort of similar system. And this is applicable to any formal system that wants to mimic number theory. But a little bit of a disclaimer, Godel doesn't actually completely rule out the possibility of finding what is called a finistic proof. basically a proof that it doesn't talk about like infinite amounts of statements and operations. It doesn't actually prevent that from happening, but he showed that if such proof existed, it cannot be mirrored in PM. And so that proof is a lot of people don't really know how to even think of that. How can you create a proof about number theory that cannot be actually mirrored in number theory? And so it doesn't really rule it out, but it does make it very unlikely for someone to actually come up with a proof of the consistency, which would have to be outside of PM. And some proofs of PM actually exist outside of it, like mathematical proofs of PM, of the consistency of PM actually exist, but we have ruled out the possibility of them being inside, within PM itself. And so this is basically the whole proof of it. And any questions?
Yeah, I had a question. So it seems like, so the way that you qualify the truth of the statement is using the grammar of the logic system, right? Without looking
the
at
truth? No,
yeah,
the grammar of the formal system just gives you whether a statement is valid. After that, if the statement is deducible, we know that there is a map that tells us that it would be true for us in like in our sense of number theory.
Right. No, that's what I meant to say. Valid. So you're right. Validity is given by the grammar of the formal system, in some sense.
Yeah, well, the grammar and the inference rules.
The inference, right.
So,
Okay.
so something to be deducible means you take the axioms and mix them up through the inference rules.
So the question is, so what Gödel did is, it seems like it's a very convoluted way of formalizing the statement. This statement is provable, right, or not provable.
Yeah, this statement is unprovable.
Right.
Yes.
So is there a way to avoid that sort of self-referential? Because it is at the end of the day self-referential, even if we don't give it any meaning.
No, of course. Well, the point is, he was able to create that sense of self-reference only using the main things that we would need to create such formal system for number theory. Right.
Like,
so that's the thing. If you have those elements, then you can create this.
Right.
And there is no set of axioms. Even if you modify it and put in more, you're always going to have a set of true statements that are going to be completely improvable by the formal system. And this is not like because we've created badly the formal system. That is only because of the very properties of whole numbers in addition and multiplication, right? And just because of their like the way they behave or the way we want it to behave will cause this statement to be constructible. And just because it's constructible, then it kind of breaks the incomplete, like it breaks the completeness of it, and also the proof of consistency. Any other questions?
It's like information theoretic almost, the result.
Yeah.
There's amongst all of the many statements that you can write down, there's simply not enough information in your system to continue the arguments for them.
To some extent, yes. Yeah, that's
Any more
everything.
questions?
Isn't it true that to simplify Gödel's argument, actually, Turing came up with this idea of whatever, I forget the term, computable functions.
Like computability.
And then using Turing machine, which exactly calculates computable functions, it's very easy to create basically a number which is not computable, just Gödel's number. It's basically page and a half proof, I think.
I'm just kind of citing.
Well, I'm not sure it's is PM. I think it's a predicate calculus, but it's sort of the same idea. The other thing is that, don't you think that Gödel's example is very close to Russell's paradox, actually?
No, absolutely. It is mimicking
Because
Russell's
it's
paradox
formalized,
in
it's
the formal
formalized
system.
Russell's paradox, yeah.
But he's able to frame that paradox
What
through
is the
purely
Barber-
number theoretical
What is a barber to
properties.
do? Yeah.
Exactly.
Ironic
It is a
that
direct
Russell used that paradox to
mimic.
portray that, and then Gödel used that paradox back on Russell.
That is very ironic.
It's very self-referential.
And another comment is that about a month, I think, before Gödel's paper appeared, Hilbert was invited to give a radio address in the place of his birth, Königsberg. And these famous words He was talking about that we
should
must
know.
know and we will know. That's the last words of his address, because he strictly believed that every mathematical
there's a bit of
statement can be
inconsistency and
proven either
completeness.
true or false. And a month later, there was paper.
He must be really sad now in his grave.
No, he wasn't really.
However, that statement itself does not contradict Gödel still for some reason.